Hello and welcome back to Nunley Math. I'm your host, Aaron Nunley. I appreciate you joining us here today as we talk about exponential growth and decay. We're working our way through an exponents unit along with exponential functions, and now we're going to look at some specific examples of how these ideas can be used in a variety of ways in real life. Now, I personally consider this lesson to be one of the most important and most relevant lessons that we do in Algebra 1, particularly because it applies to every individual, regardless of your intention of studying future math or not. I consider it one of those lessons that's really just important for adulting, as it were, for being a grown-up, for being a successful member of society. So hopefully as we watch this video, or as you watch this video and we work through this together, you'll get an idea of why I consider this to be important and how it can be helpful or useful to you. So what I've done for my students is I've gone ahead and created a quick review. I would give them a few minutes in class to try and work through this. I'm going to go ahead and put it here for you. I would recommend that you pause the video and try these out if you're interested in making sure that your exponent skills are where they need to be in order for you to be successful at this lesson. If you are not interested, you certainly can skip ahead. If you are interested, pause the video, try these on your own, and then restart to see if what I'm doing makes sense to you. I personally am going to go ahead and work my way through these. Notice example A says x to the 7th times x to the 5th. Remember, this is a long string of x's multiplied together. This is a long string of x's multiplied together, and this is multiplication. Since this is all one long string of multiplication, the product of powers property says that really all we have to do is add those up. If I have 7x's multiplied together and 5x's multiplied together, then I really just have 12x's multiplied together. The next example, example B, says y to the 3rd to the 8th. This says I have 8 groups. Every group is multiplied together, and within every group you have 3 y's that are multiplied together. So 3 y's 8 times the power of a power property says you have 24 y's multiplied together. Example C, you've got 9 to the 5th over 9 to the 8th. This is a quotient of powers property. It says that you just have to subtract those exponents, giving you 9 to the negative 3rd. Remember that an exponent problem is not considered simplified if it still has a negative exponent. A negative exponent says use the reciprocal, so this is 1 over 9 to the 3rd. Now you could actually go ahead and do 9 to the 3rd, which is 729, and get 1 over 729 if you wanted to as well. I didn't do that here today. D is a little more complicated. Notice you have this negative exponent on the outside. A negative exponent always says use the reciprocal, so I use the reciprocal of the value in parentheses. And then since I have a square on the outside, I need to square everything on the inside. 1 times 1 is 1, 5 times 5 is 5, a to the 3rd times itself is a to the 6th, b to the 5th times itself is b to the 10th. We then talked about rational exponents and how if you have something to the 1/3 power, that is the same as the cube root. So this is asking what times itself again, or 3 of what number multiplied together gives you 64, and that's just a 4. 4 times 4 is 16, times 4 is 64. Notice that because this is an odd root, that negative 4 would not work, because negative 4 times negative 4 times negative 4 would give you negative 64. And then one more with the rational exponents. Notice that it is negative, which means use the reciprocal. If you've got 3/4, the bottom number is the root, and the top number is the exponent. So we're saying, what is the 4th root of 1 over 81? Then do that to the 3rd power. Notice the 3. Notice the 4th root. That is the 3/4. 1/3 times 1/3 times 1/3 times 1/3 is 1 over 81. We'll do this to the 3rd power. That's 1/3 times 1/3 times 1/3, which is 1/27. Hopefully you did well with that. If not, we do have a whole series of videos on exponent rules that you can go back and take a look at. I'd encourage you to do that if you had trouble. We then talked about the exponential function, and we said when we look at a table and we're trying to create the exponential function, we're first going to look at the rates of change. Notice that from 50 to 60, that is a growth of 10. 60 to 72 is a growth of 12. 72 to 86.4 is a growth of 14.4, and 86.4 to 103.68 is a growth of 17.28. Now, if this had been a constant rate of change, I would have known that this was a linear function. But as it is, this is a rate of change that is continually growing. Because of that, what I want to do is I want to find out if it is growing by a constant factor. So I take my 12, divide it by my 10, and I come up with 1.2. I take my 14.4 and divide by my 12, and I come up with 1.2. And I take my 17.28 divided by the 14.4, and it comes up as 1.2. In fact, 50 times 1.2 is 60. 60 times 1.2 is 72. 72 times 1.2 is 86.4. And 86.4 times 1.2 is indeed 103.68. So this is our common factor. We're going to be multiplying through it every time. The pattern for an exponential function says you have a starting value and you multiply by the same number over and over again. Well, in this case, my starting value was a 50, and I'm multiplying by 1.2 repeatedly, which means my function is this: 50 times 1.2 over and over again. I do something similar to that with the next one. I look at the difference between these. 85 plus 51 makes 136. 136 plus 81.6 is 217.6. 217.6 plus 130.56 is 348.16. Plus 208.896 is 557. Once again, you can see that my rate of change is continually changing, so it's not linear. I'm going to look and see if there's a common factor. 81.6 divided by 51 is 1.6. 130.56 is 81 divided by 81.6 is 1.6. And 208.896 divided by 130.56 is 1.6. Notice you have that common factor. Our rule is take your starting point and multiply by that common factor over and over again. Remember, an exponent is just repeated multiplication. In this case, I started with 85. So my function is 85 times 1.6 to the x. Here again, I did that very quickly, and I am aware of that. The reason for that is this is not a lesson on these topics. Instead, this is just a review that I wanted to give you before we began, because it's what I ask my students to do in class. It does cover some things that are going to be important for us as we talk about exponential growth and decay. Here's a sample problem for you. You put $1,000 into a mutual fund that averages about 8% growth per year. Complete the table to show how much money you would have at the end of each year shown. This is why I think that exponential growth is such an important concept for us. It's because this is the basis for how our investment and savings system works. When you invest money into a CD or a stock or a mutual fund or a 401k or something like that, your goal is always to gain extra money. You're investing your $1,000 in this case, and you're hoping to earn 8% growth per year. Now, we don't know ahead of time that it is definitely going to earn 8% growth per year. It might earn a little more, it might earn a little less, but when we say it averages 8% growth per year, typically that means that over the course of 5, 10, 15, 20 years, this is what is averaged out. So we can use it to make predictions about our future. When you take money and you invest it, your goal is to set this money aside for some other purpose, most of the time being retirement. And a lot of people don't understand how the money they set aside for retirement ends up growing and becoming more money. That's what we're going to talk about today. And here's the way this works. If we set $1,000 into our mutual fund, I'm going to go ahead and put that $1,000 down. That $1,000 at the beginning is all in the same fund. I put 100% of it into this one fund. Now, big picture, you should never put 100% of your money all in a single fund. You should diversify and spread it out over a lot of different funds just in case one of those doesn't work out. But this $1,000 is all going into this fund, 100% of it. Hopefully I've got $1,000 going into some other fund as well. Since it's $1,000 and it's all going into the same place, I've put $1,000 into my investment, which is a total of $1,000. Now, I know this probably seems a little redundant. Why did I bother to do this? But it does lead toward the next idea. First is we want to understand that percents can be written as decimals as well. So this $1,000 goes into this mutual fund. At the end of the first year, I get my $1,000 back, plus if things have worked out the way they're supposed to, I'm going to earn 8% of that $1,000 as well. I get all of this back, and hopefully I've earned more money. In this case, 8% more. Does that make sense? I get all of this, 100% of this, and 8% more. Notice I've written that as a decimal. Another way to put that is to put a times 1 in here like I did before. That's 100% of the 1,000 and 8% of the 1,000, or 108% of 1,000. Notice I use the distributive property. I said 100% of 1,000 and 8% of 1,000 is 108% of 1,000, or 1.08 times 1,000, which is $1,080. I had $1,000, now I have $1,080 because I have gained value. That's the goal of the mutual fund, is to take your money, set it aside, and allow it to work to earn more money without you having to do anything with it. That's how investments work. Let me run through that one more time. The next few will go faster. I just want to make sure we understand this. We had 100% of our 1,000 combined with 8% of our 1,000. I then just rewrote it as 100% in decimal form and 8% in decimal form. And I used my distributive property to say, well, if you have 100% and you have 8 more percent, 108 is 108%. In decimal form, that's 1,080. Now, here's the cool thing about exponential growth. When I start year 2, I don't start off with $1,000 like I did at the beginning. That $1,000 went in, it gained extra money, it gained $80 extra, and at the beginning of my second year, I don't have $1,000. I have $1,080. That investment is going to sit in there, and it is going to gain 8% as well. I left it in for a year and got 8% more. That's what I had written here. And then because I'm leaving it in for another year, that new amount, that $1,080, gets multiplied by 1.08 as well. In other words, I've now multiplied by 1.08 2 times to get 1166.40. Notice the first year I only had $1,000 and I gained $80 in interest. But the second year I didn't gain $80. I gained $86.40. I gained more because the second year I started with a higher amount. Now, what's really cool is when I start the third year, I no longer have $1,000. I no longer have $1,080. I now have $1,166.40. So I take that, I leave that alone, and that is going to gain 1.08. In other words, I'm going to get 100% of that back and 8% more. Written out the long way, I had $1,000, I left it in for 1 year and I gained 8%. These two multiply together to give me the 1080. I then left it for a second year and I had that 1080, this, multiplied by 1.08 again to give me the 1166.40. So this is the 1166.40. I'm going to take that times 1.08 for the third time. This is what I had after 2 years. Multiply it by 1.08, that tells you what I have at the end of 3 years. Notice it's $1,000 times 1.08 3 times, giving me $1,259.71. Hopefully this is starting to make sense to you, because I'm just going to repeat the same process over and over again. I have $1,259.71 at the beginning of the 4th year. I keep 100% of it and gain 8% more. Written out long way, I started the year with all of this. Notice that's what's on the previous line. And then I take that and I multiply it by 1.08 again. This is for the 4th year, or the 4th time. $1,000 times 1.08 4 times is $1,360.49. Now, I can keep doing this, and every year I just stick on another times 1.08, and I get a new value. Do it again. 1.08. That's 1,000 times 5 1.08s is what I started the year with. Multiply it by another one, and I get 1586.87. Are you starting to see how exponents play a part here? We're just keeping track of how many times we gained 8%. Our 100% we started with plus 8% more. 100% we started with plus 8% more twice. Now, I am going to go ahead and fill this in. Notice that at year 0, I had $1,000, but it had not grown by 8% yet. So I could say it's times 1.08 to the 0 power. There again, this is another reinforcement of the idea that anything to the 0 power is just 1, and 1,000 one time is 1,000. Also, I could put a 1 in here as well, since I had the 1.08 once. Here's the good news, that the first year I had $1,000 and gained 80 to get $1,080. The second year I said I'd gained 86.40. The third year I gained 93.31. The fourth year I gained 178, 108.84, and 117.54. I put this up here because this does something that's very, very important. Notice that I started off growing only a little bit, but every year the rate of increase grows. Remember our exponential functions? When we graph an exponential function, what always happens is you start off, see if I can come up here and make some, you start off growing slowly, but then your rate of growth gradually increases over time. That's what's going on here. I start off growing slowly, but then I gradually increase that over time. So what does that mean? Well, let's jump down here to 10 years. In year 10, I'm going to have that $1,000, and I will have multiplied by 1.08, or I will have gained 8% 10 times. If I type that in a calculator, my $1,000 in 10 years has turned into $2,000, $2,158.92 exactly. If I were to go 15 years, if I did 1,000 times 1.08 15 times, I end up with 31.72. If I do it 20 times, notice it's to the 20th power, I've got $4,660.96. And if I jump out 50 years, I end up with $46,900. 901.61 actually. Notice what's happened. I took $1,000 and I invested it in a high-quality mutual fund, and if I can maintain that 8% every year, in 50 years, my $1,000 turns into $46,000. That's the reason this lesson is so important for us as individuals. It's because if you hope to have enough money to retire on someday, if you want to have lots of money in retirement, the key is not so much how many dollars you stick in. The most important thing is that you stick it in early so it has lots of time. Because when we talk about exponential functions, early on things always grow slowly, but the more time you have, the faster your money grows. That's why a student coming out of college who invests $1,000 and can leave it there for 30 or 40 years is so much better off than students who come out of college and buy cars and buy new phones and buy Xboxes and don't start saving until much later in life. Because if you can only leave your money in the bank for, or in the investment for 20 years, you only have 4,000. The growth happens farther out in time. Very important lesson for us. Now, I want to take a look at a couple of the things. Here's a second example, and then we're going to tie this together in terms of exponential growth functions and exponential decay functions. It says, suppose you take out a $50,000 student loan. That's your starting amount. As long as you're in school, you don't have to pay the money back, but the bank charges you 3% every year. We want to give an equation that shows the total amount you owe after X years of not paying the debt. And then we're going to calculate how much you're going to owe in 10 years. Now remember, the last example of exponential growth of an exponential function was talking about how much money we save. But exponential growth happens on money you borrow as well. The downside is that when you're borrowing the money, the faster it grows, the more money you have to pay back. So here's what we're going to do. If you remember our exponential functions, we said y equals a, our starting amount, times some rate of growth to the x power. When we talk about exponential growth functions, you still have that starting amount a, but notice your growth rate is listed not as b, but as 1 plus r. That's because you're always going to have the 100% you started with plus some percentage growth. And then notice they changed their x, their time, into a t for time. So this is basically the same function. It's just we have to calculate this growth factor instead of it just being given to us. Let's come back to our initial example. Y equals the amount we're going to owe equals whatever we started with. Well, that's the $50,000. $50,000. Times, ordinarily we would have a growth factor here. But in this problem, what they told us is that it's growing by 3%. That is not the same as our multiplication factor because we have to pay back 100% of that debt and we have to pay 3% more every year for t years. Notice that's our function. $50,000 times 100% plus 3%. We have to pay it all back plus 3% more, and that's going to grow every year. Notice my slide had these backwards, but that's okay. 1 plus 0.03 is 1.03, and we said we're going to do it for 10 years, which gives us $67,195.82. Notice that $50,000 student loan has increased by $17,000. Remember, this is money you owe. The longer you let it sit in the bank, or I should say you let it sit in your account or in your debt, the longer it sits there, the more you're going to owe. That's why you're so much better off to pay it back in 1 or 2 or 3 years than you are to wait 10. That's also the reason why the bank is very willing to let you sit there and not pay it back for the entire length of your college. Because the longer you don't pay it back, the more they know you're going to owe them. That's an example of exponential growth. Now, we do have exponential decay functions as well. They are exactly the same, but instead of something growing, it's going to decrease. The only difference is we would be subtracting the percentage instead of adding it. By the way, I did go through and list that with real nice, neat numbers, and I boxed it so you could see the answer. Let's take a look at this. You deposit $300 into a savings account and you earn 4% interest. Notice we're earning, so this is going to be exponential growth. Write a function that shows your balance at the end of t years, and then what would your balance be at the end of 22? Let's walk through this again. We are going to start off owing 300. We have to pay 100% back, but they're also going to charge us 4% more, which means we're going to have to pay back 104% every year the entire time we owe the money, in this case 22 years. And of course, anticlimactically, the slideshow was out of order, and you're going to end up owing 78, 20, 73. And I'll write that out as a nice, neat number. Look over here. The value of a car is $15,000. That's the initial value. Notice it depreciates or loses its value at a rate of 10% every year. Write a function that shows its value after t years and how much would you owe after 5 years. Now this one is interesting because this is the first time we are losing value. So initially it's worth $15,000. $15,000. It's worth 100% of that, but after each year it loses 10%. In other words, it's going to be worth 90% of what it was worth the year before. 90% of what it's worth the year before. Notice 100% with a 10% loss is 90%. Since we're losing that 5 years in a row, it's going to end up having a value of 88.5735, which there again I boxed up real nice for you. I would recommend that you pause the video and try these two on your own. They're the exact same types of problems. You should be able to work through them pretty easily. I'm going to go through them quickly since I'm going to assume you've already done this. You start off with 80,000 people at the festival. It increases 6% every year for t years. How many would be there in the 8th year? Well, I start off at 80,000. 100% of those people come plus 6% more every year. Once again, the anticlimactic bad slideshow. 80,000 people times 1.06 for 8 years comes out as 127,500, and we'll approximate that as 8 people. Over here, you take 800 milligrams, your body absorbs 29% per hour. If your body is absorbing it, that is a loss. So this is going to be a decay problem. I'm going to write a function for t hours. How much is left after 3? Since it's a decay, we're going to lose 29%. There's the anticlimactic solution. 100% with a 29% loss is 71% remaining every year for 3 years. And of course, I rounded that off and made it nice and neat and pretty for you, and I boxed it so it's easy to find. Last thing I want to talk about is making sure we can tell whether something is exponential growth, exponential decay, or neither. At first glance, you can tell that this is not going to grow. It is going to be some kind of decay. But in order for it to be exponential decay, it has to have a common factor. So I'm just going to look at these. 90 over 270 is 0.33. 30 over 90 is 0.33. And 10 over 30 is 0.33. Obviously, that's 1/3. I did go ahead and round it off. That means that this will be an exponential decay. Since what's left each year, or each day, or whatever the time frame is, what's left each time is 33%, the function here is the 270 starting, I had 100%, and I lost 67% every time. See how that works? Now, if we were just doing exponential functions, this would be 270 times 0.333, there again, rounded off, to the t. But because we're looking at the decay, I wanted to see the 100% and what was being lost off that 100. The second one, 24, 12, 6, and 3. It can't be growth, so let's see if it's exponential decay. 12 over 24 is 0.5. 6 over 12 is 0.5. 3 over 6 is 0.5. So it is going to be an exponential function. In this case, it's exponential decay because it's going down. And your rule is you started at 24, you lost 50% every time. How about this one? 5, 10, 20, 40. 10 over 5 is a growth of 2, 2, and 2. This will be exponential growth. If I were just writing an exponential function, this would be y equals 5 times 2 to the x. But since I'm looking for exponential growth and decay, we have to remember that it will be 5, but if it doubled, we had 100% and we gained 100%, which is where that 2 comes from. Notice it's repeatedly every time. Here again, I'm going to go ahead and wrap this up because I know the video is starting to get just a little bit long. I would recommend you pause the video and try the next 3 on your own. I'm going to do them pretty quickly for you. This is 25%. What's left is 25% of the original. That is decay. Notice that is 100% and then a 75% decay or decrease. Take a look at this next one. You'll notice that it does grow by 7, but notice that x grew by 2. So this grew by 7 halves. This grows by 7 halves. And this grows by 7 halves. Y grows 7 every time x grows by 2. This is a constant rate of change or a slope of 7 halves. This is going to be a linear. If you're ambitious and you wanted to find this equation slope-intercept form, you could use your point slope formula. Notice that this one has a factor of 10 every time. That does make it exponential growth. And y equals, starting at 4, I have 100% plus 900%. 1 plus 9 makes that 10 to the t power. Hopefully this has been useful to you. I know a few of these we did pretty quickly, but that should give you a pretty good idea of what's going on. We were going to talk about exponential growth and decay a little more in the next slideshow as well, so please come back and join us for that. As always, thank you so much for watching. We do appreciate you taking the time to be here with us. Make sure you leave us a comment in the comments section. Please like and subscribe, and make sure you turn on those notifications so you don't miss anything coming out of Nunley Math. As always, best wishes